Hello everyone, today I am going to show you the working of the speech command model which is present in this given link. So first of all, I mounted my drive into this because I am going to save the results in my drive, and now I git clone this repository. So let me do this. It has been done. Let me change it to the directory aim.ml where our dataset is present in this directory, speech command model /data /Pradeep. So as you can see, now I have downloaded the dataset, and my directory is here, AIML folder, speech command model, data, Pradeep 16. These 5 folders will be my labels for the dataset: back, forward, left, right, and stop. Okay, and these are the dependencies. This will be a pre-processing library Capre. We will extract features from our training and testing data and use it in building the model, and we will use this sound file library for reading the sound files given in these folders. So let me import them. So now I will be loading the data in a temporary xtemp in ytemp because I will be augmenting them later on. So then on I will create a final htrain and ytrain data set. So what will this do is, this OS list directory will list all the directories present in this particular folder, and then I will iterate in this folder and read this file one by one. I will use that sf.read. It will returns data and sample rate, and I will append them in xtemp in ytemp, and then I will be converting them into a numpy array because of speed advantages. These are my xtemp and ytemp. As you can see, I have 0, 1, 2, 3, 4. That means 5 labels for my data set: back, forward, left, right, and stop. Let me check out the length. I have 400 samples and length of xtemp 0. That means for every data point I have 16,000 features. And now I will import train test split. I will do this splitting part. I have used an test size of 0.2, and I have used random state. I have used stratify so that I get equal proportions of splitting. Let me check out the training shape. 16,000 and 320. We get 320 data points in training part and 80 points in testing part. Now we will perform augmentation of data. Why we are performing augmentation of data is the fact that in deep learning models we achieve over fitting very easily. So as you know, to build a more sophisticated model which performs better on the test data, we are going to do augmentation, and we will be shifting 25,000 vectors of zero length of zero values, zero entries, and we will creating 18 files per sample. How come we are coming to this 18 value? I will give this calculation here. So I will be enumerating in the training data, and I will get length of j. J is my data point. J is changing and so is a. But as we can see, every point in H train is 16,000. So that means a will always be 16,000, and I will be time shifting the values. So I will be performing another nested loop inside this main loop, so as to as value of b changes, my value of training part in this length vector of length 25,000 changes, so that I can get a time shifted sample. So how come I get this 18 times value? I took a vector of length 25,000, I subtract length of a, which was 16,000, from this I get 9,000, and I am running this loop 500 times. So that means total times my loop will be 18, 9,000 by 500. Inside this loop I create a np zeros array of 25,000. I changed this part of this numpy zeros array from b to b plus a. That means a length of a part between this from this index to b plus a index. As we can see, length of this part will be b plus a minus b, that means a only. But as b will be changing, so it will be shifted as again and again as the loop progresses, and I will be feeding j. J was my H train part, right? So now I append this in H train and Y train. So now I will be predicting that I will get total number of samples will be 18 into length of H train, because for every loop, this loop is running 18 times, and this loop will be running length of H train, that was 320. 18 into 320 times. I convert them into H train. I perform the same process for testing data. So let me check the so this is my shape that as I told earlier, 320 which was length of H train, we get it from here, into 18 we get it as 57660. That means our loops have performed as expected, and we have got a feature length of 25,000. So we have increased our feature length by almost 9,000. So that part was our augmentation. Let us check the unique values in Y train 0, 1, 2, 3, 4 as expected. Now we import the TensorFlow libraries, layers, sequential model, and this Capre for pre-processing. Okay, and what we'll be doing is it is used like a Keras model only. What we'll be doing is we will be creating these layers and fit the data and predict it back. So as our H train changes now from here, we will get extracted features in our new H train and H test. So let me change the directory. Sorry, I didn't run this now it should work fine, I guess. So now it is working fine. I forgot to ran this tab. So now we have saved. As you can see now, our directories is being updated, right? Our X train and Y train are saved right here. After refreshing this, refreshing the files, we get MFCC train, which we derived from Capre. Now let us build our model. We created a function attention model, and the input will be taken through this. We create a layer which contains the H-train shape part. Now this input layer will be feed into this convolution 2D layer, then a batch normalization layer, then again a convolution 2D layer, again a batch normalization layer. We reshape the part to squeeze it. We propose a 64 units in our LSTM layer. So this is now feed it into this LSTM. We calculate the unit importance, we calculate the attention, and we finally send it for the output layer. We create a model with this input equal to inputs. This was our inputs, and output equal to this, and we named our model attention. So we return this model, we call this model. Now model will be created inside this variable. We compile it, we use Adam optimization, we use loss sparse cortical cross entropy, and same for metrics. Okay, and let me summarize the model. As you can see, convolution 1 layer, input layer, convolution 1 layer, first normalization layer, second convolution, second batch normalization. We squeeze the output from this convolution 2D layer. We created an LSTM sequence. We created a final sequence for unit importance, calculating unit importance and attention scores, and finally a dense layer, and then an output layer. We fit our model, considering an batch size of 15 and 5 epochs, and after fitting this data, we will be going to predict our graphs, and what we are going to plot the XTest data into this and compare with the let me see. So I think our model is running pretty good, 0.97, 0.99, and it is approaching, it has overfitted, which we did not wanted, but let's guess it will require a bit more augmentation, or we will require more data. As we had only 400 data points, it will require almost 1000 data points according to my estimate. So our final accuracy was 0.9931. Now these are the graphs we get from of the logarithmic values of the predicted data by feeding the H-test data into this. So I hope my explanation was clear for you to understand this. Thank you.